Thank you very much. It's a pleasure to be here at GGI and a pleasure to have you all here in the audience for this school. As you know, this is being recorded, and despite that, I hope you take the opportunity to ask questions and don't worry about anything that you say on the camera, being embarrassing. I assure you that all the mistakes that I'll be making on the board are going to make any question that you ask seem highly intelligent by comparison. And this is, a passion of mine, thinking about collider physics, thinking about QCD. It's something I'm really excited about, and I hope to have a chance to engage with you either in the room right now or certainly later on this week. So there's going to be 4 lectures, and my rough plan is to first, in this lecture, give you an overview and inspiration of this field. And then in the second lecture, try to show you a little bit of the nuts and bolts about how collider physics is put together by showing you how you can go from Feynman diagrams to cross-sections in a couple of examples. I want to give you an introduction to my own subfield, which is the field of jets. I'll tell you what jets are, tell you how you reconstruct them and how you study them at the Large Hadron Collider. And then hopefully I will have saved enough time so I can give you a case study in my subfield, the field of jet substructure, which is an area that's grown enormously over the past decade. But let's start with an overview and an inspiration, and maybe start with a very basic question of why colliders? What do we do at the Large Hadron Collider, right? We take beams of protons, we slam them together, and we've had a half century to go to ever-increasing collision energies to try to understand the structure of fundamental physics. And you can ask, is this a good strategy? Colliders are expensive. Is this expense worth it? And to my knowledge, this is the best, at least known strategy for us to study heavy objects that are short-lived and produced rarely. And if you have lighter objects that are longer lived and they're produced more copiously, there's other strategies that you could try to use to study them. But in this case, we don't at the moment, have a better strategy for understanding objects like this, and colliders are our best approach. And again, if you come up with a better method, you will revolutionize particle physics. And indeed, there was already a revolution that earlier you would take beams and slam them into fixed targets. And the realization that you could slam beams against each other and actually capitalize from the larger center of mass collision energy that's available when you do this colliding beam, that itself was an advance. And maybe there's another advance on the horizon that you can think about. But just as an example, if I want to think about a particle like the Higgs boson, does it satisfy these criteria? Well, yes, it's a heavy object. The mass of the Higgs boson is around 125 gigaelectron volts. Its lifetime is short, so if I convert its lifetime into a length scale, it's not quite the same length scale, short length scale that Rafael told us about earlier today, but it's quite short, 5 times 10 to the minus 11 millimeters. And the cross-section is relatively small. So the cross-section for Higgs production at the LHC, which we'll talk a little bit more about in a moment, is around 50 picobarns, and I'll explain more what a barn is. But for studying something like the Higgs boson, if you want to directly understand its properties, I know of no other way than slamming together particles. So that justifies, in some sense, the collider physics part of these lectures. So now you can ask the question, okay, well, why QCD? Why do I care about the dynamics of QCD? I mean, especially, let's say I care about the Higgs boson. The Higgs boson participates in the electroweak interactions. Why should I study QCD at all? Well, of course, we're slamming together protons. And protons are basically a bag of quarks, antiquarks, and gluons. And so inevitably, if you're trying to study collider physics, at least in the context of hadron colliders like the LHC, inevitably, QCD dynamics, the dynamics of the quarks, antiquarks, and gluons, play some role. And it ends up being challenging. And if you want to understand something like the Higgs physics, you have to deal with the challenge of QCD. And in particular, when these quarks and gluons are liberated from the proton, they give rise to all sorts of interesting dynamics that can end up being the backgrounds to something like you're studying like Higgs physics. Or if you're someone like me, just the dynamics of quarks and gluons themselves are intrinsically fascinating. And I'll try to tell you more about that in the last 2 lectures. Now, I want to demystify one aspect of collider physics just at the beginning, which is that collider physics is just an application of quantum mechanical scattering theory that you might have already studied in an undergraduate class. So collider physics is basically just scattering theory. And so what are we trying to do? We're trying to start with some initial state. And at the LHC, this initial state are beams of protons. You have a plane wave of protons coming one way, a plane wave of protons going the other way. And that's the state of the system at, let's say, some early time. So time t equals minus t, capital T. And eventually, we're going to take the limit where we take the time off to infinity. But you start at some time t with some initial state, initial beams. You evolve your state to some final state, some out state that you're trying to study. And then you're just asking, in my detector, what is the set of all possible out states that I care about? So you might have to integrate or sum over all possible out states. This is the state, again, that I'm hitting at t equals plus t. And then you take the long time limit, and this is just a classic scattering problem. Now, when we teach it in quantum mechanics class, we often are doing a lot of scattering, where the same things coming in are the things coming out. In this case, it's very inelastic. I start with protons here, and what comes out can be a complicated array of hundreds to thousands of particles. But at its heart, this is all we're doing, with one additional feature that will become prominent in these lectures, is that we have to choose a weight for my out states. I have to choose what am I studying and what I'm not. So if you imagine this weight being 0 or 1, 0 means I don't care. 1 would mean that I care about everything. And indeed, if you put 1 here, then the sum over all these states turns into the identity matrix. And I forgot to square this. The sum over all the out states of ket bra turns into the identity matrix. This thing goes away and I get 1. So there's a 100% probability that something's going to happen. But if I choose weights for different out states in different ways, I can expose different aspects of the field theory that I'm trying to study. And the key to collider physics, in some sense, is this choice of W out. And so the goal, or the key to collider physics, is you want to choose which states you want to sum and integrate over. Which states do you consider as being interesting? Again, if you really included everything, then you learn nothing. So if you say, I want to know what's the probability for something to happen, this formula doesn't give me any insight. 100% chance that something's going to happen. What I care about is I care about the difference in probabilities for different types of outcomes. And so I want to choose my weight for each of those outcomes differently, depending on the type of physics that I'm trying to study. And what your hope is that you've chosen values here that are physically interesting, that is, you actually learn something about the dynamics of your theory by doing this measurement. I mean, there's plenty of things that you can measure where you would learn nothing from having done it. You kind of just imagine choosing random numbers here. What would I learn about the structure of the universe by just choosing random weightings for the different final states of interest? So you want to choose something that's physically interesting. You want to choose something that you can compute theoretically. So I'm a theoretical physicist, and I like to be able to make predictions about what will happen. And if there's no way for me to do a pencil and paper or chalk and chalkboard calculation or even a numerical simulation to try to understand what the answer here might be, I'm not going to learn anything on the theory side. And then this is another key. You have to be able to measure it experimentally. And there are plenty of choices that I could make here for something that I would care about what the answer was. But experimentally, I don't have access to it. And so you have to think about the detectors that you're using to ask whether it's possible to gain insight or access to this quantity. But as I'll explain more later, there's kind of a master formula that we have in collider physics, which is essentially just a fleshed out version of this, but it's just scattering theory. You choose in states. In this case, someone has chosen it for you at the LHC. You give colliding beams coming in. And then you have to say, what out states can I measure? Sum over everything, weighted in some interesting way. Hopefully, you gain insight to the fundamental structure of the universe that way. And indeed, this is the type of formula that was used for the discovery of the Higgs boson in 2012. Now, let me just pause for a second to see if there's any questions. So QCD dynamics plays a key role in this problem here. So let me give you an example of a question that you could ask where QCD dynamics matters. So let's say you asked, tell me, when I slam together protons, how often do I get 37 neutral pions, 31 positively charged pions, 29 negatively charged pions, 10 negatively charged kaons, 10 positively charged kaons, and 2 neutrons? What is the probability of that? So I could change this problem slightly and make it much easier. So if I say what's the probability of getting 3 neutrons, then in this case, I would have proton-proton that has baryon number 2. None of these carry baryon number, and so the probability of getting 3 neutrons, to the best of our knowledge, is 0, at least in the standard model, since baryon number is conserved. So okay, let's make it non-zero that way. And protons have charge 1, so this side has charge 2. And so here, if I've done it right, okay, these don't count, these balance each other. Ah, yes, 2 extra charges here, so at least I know it's not 0 just because of some conservation law. But, you know, if you ask me to predict this rate, this is a very non-perturbative question in QCD, and I don't really have any hope that I could ever answer a question that's this intricate or detailed. And so that's a question that I don't, to my mind, maybe some people would find it interesting, but to me, I don't think it's that physically interesting. I don't know how to compute it theoretically, and also experimentally measuring that is extremely challenging. For various reasons, but one of them is that actually telling the difference between pions and kaons is not so easy to do experimentally. And also, here I didn't give you any specification about the energies of these particles, and I could have a really low energy particle here that I'd have to include in the sum for that way of defining it, but experimentally it would be very challenging to measure arbitrarily low energy particles. So, okay. This is not an example of something that I want to study in these lectures. Rather, I want to choose observables, choose the type of measurement that I'm doing, choose this weight function if you want to think about it in this language. I want to choose observables such that when I do a sum over all the different things that can happen with hadrons, with all these pions and kaons, for proton-proton going to all these various hadrons, weighted in the appropriate way, that I can replace this with a calculation that has to do with quarks and gluons, that I can replace it with one where I can do a sum over partons of proton-proton going to some partonic final state. And this squiggles will be complications that we'll deal with later in these lectures. But I want to have observables. I want to choose measurements that this approximately holds. And if this holds, if I can map measurement, my measurement, as I'll explain more later, has to have to do with these pions and kaons. If I can match it onto something that does deals with the dynamics of quarks and gluons, I have a chance of computing it theoretically. And so we want to choose observables that will make that possible. And so a lot of these lectures are about the choice of observables, which ones we have theoretical and experimental access to. And so more formally, what we want are factorizable observables. So there's no way to get around the fact that QCD has non-perturbative dynamics, but factorizable observables are ones where you can more cleanly separate the dynamics that's perturbative, the one I can calculate using Feynman diagrams or amplitude techniques, versus non-perturbative, of course, both of these are QCD dynamics. But if I can separate out the perturbative and the non-perturbative piece, I can hope to do a precision calculation on the perturbative side and then use various strategies to try to gain access to non-perturbative information, possible by doing measurements in an auxiliary system and then mapping it to the system that I'm trying to study. But it is not obvious at all that you can come up with observables that have this property. And one of the challenges, but also one of the opportunities in collider physics, is that the choice of observable matters, and there's creativity that is necessary to find observables that have this mapping. And the field of jets and jet substructure that I'm a part of, a lot of that progress in those areas has been coming up with different types of observables, different ways that respect this mapping, but give us new insights into the theories that we're trying to study. And we've known about jets for 4 plus decades, 40 years or more. But we're still finding creative new ways to analyze collision debris, and maybe one of you will come up with a even cooler way to process LHC data to expose new dynamics either within the standard model or potentially beyond the standard model. Question, yeah?
Does the definition of jet depend on what you're looking for? Do you change that from what process you're looking for?
So the question was, do I change the definition of a jet that I use depending on the process that I'm trying to study? And the answer is yes. You, as the user, get to choose what you measure. Don't let someone from the past tell you, oh, you must use this particular jet strategy. You choose the jet strategy or the way that you want to analyze the hadronic final state to gain access to the information that you want. And so there is no intrinsic fundamental jet definition. There is no God-given observables that we say are better than other ones. Depending on the physics process that you want to study, there might be different analysis strategies that you want to use. And it's that freedom which both makes collider physics exciting, but also makes it seem a little bit less pure because, again, you have to make a decision on what you measure. And so there isn't really a notion of just tell me what some kind of fundamental cross-section is. It depends on your measurement, it depends on your calculational strategy, and it depends on your observable strategy. Okay, so let's just give some numbers to give a sense of scale of the problem that we're trying to solve here. And while I'm erasing, feel free to interrupt me with further questions that you have. And you don't have to raise your hand, you can just shout it out. So let's just put some numbers to get a sense of scale. So the current heavy hitter collider, it's, by the way, not the only collider in the world. There are other colliders in the world, but this is the one that we hear most about, proton-proton collisions. And what are the center of mass energies that the LHC operates at? Well, it did initial running at 7 TeV, upgraded to 8. Last run was at 13 TeV, eventually 14 TeV. So these are high energy scales, and you need these high energies to be able to access heavy particles like the Higgs boson. What's the collision rate? So the collision rate, these protons slam together every 25 nanoseconds. So every 25 nanoseconds, you get a proton-proton collision. Something will happen. Another 25 nanoseconds, something else will happen. That corresponds to a collision rate of 40 megahertz. The number of protons that collide at a time, so this is the protons per bunch. So at the LHC, you don't just collide one proton against one proton. You actually slam together bunches of protons. And the number is astronomical. in a literal sense. So it's 10 to the 11 protons per bunch. And the reason why I say that's astronomical is that's similar to the number of stars in the Milky Way. So you can imagine the stars in the Milky Way, the stars in Andromeda. Eventually our galaxies will collide. And the number of binary stars that will hit each other when the Milky Way and Andromeda eventually merge, that's roughly, at least order of magnitude wise, the number of proton-proton collisions you get when these bunches pass through each other. So these proton bunches are mostly empty space, and you get, depending on how fine you've tuned your beam, maybe 1, 5, 10, 20, maybe really squeezy, you get 50, 100, 200. But that's to even just get collisions at all, or non-elastic scattering, you need to have this high bunch content, proton bunch content. So we often talk about at colliders, what is their instantaneous luminosity? So the instantaneous luminosity is just saying, I have two bunches colliding. How many particles are in bunch 1? How many particles are in bunch 2? What is their frequency? That's 40 megahertz at which they're colliding. And then in what relative area are those beams being squeezed into, some kind of effective area? And at the LHC, the effective area is something like 0.1 millimeters, that whole thing squared. So a proton, as I'll explain more in a moment, has roughly a 10 to the minus 15 meter size. So these beams are relatively big compared to the protons themselves. Again, it's mostly empty space, just like the galaxies are. And a typical number for the LHC that people will talk about is like 2 times 10 to the 34 in units of per centimeter squared per second. And that's the instantaneous data taking rate is proportional to that. And then we talk about integrated luminosity. That's just taking your beams, keep running them, and ideally over the course of a year your beams would be always on. But this is like the actual uptime that you're actually colliding beams, which is roughly something like 2 months per year. We are actually colliding. And so you can take roughly 2 months per year times this luminosity here, and what do you get? You get a number that's like 100 inverse femtobarns per year. And that's roughly the data taking rate that was achieved during this last run 2 of the LHC, and we'll get a little bit higher for high luminosity running than that. But you're collecting a substantial amount of data, and just to give you a sense of what that data taking rate is, let's convert this into a number that's maybe a little bit more intuitive. So this is a lot of data. How much data is it really? Well, let's just ask how many roughly interesting collisions have happened where instead of the protons just passing by each other, something happened. So we can try to estimate this the following way. So we can ask, what is the radius of your proton? So the radius of a proton is a femtometer, roughly. So 10 to the minus 15 meters. And if I want to convert this in natural units to an energy scale, it's has a corresponding energy scale of 200 mega electron volts. The proton radius is convenient it is convenient to talk about cross sections in units that are kind of close to the proton radius. So a barn is a unit that we use to talk about cross sections. And a barn is 100 femtometers squared, so that is units of an area. So 10 to the minus 28 meters squared. And you can see that if I take a proton radius, if I square this, 10 to the minus 15 squared, gives me something not quite at 10 to the minus 28 meters squared, but somewhere around there. So, barns are nice units if I want to talk about kind of the cross-sectional area of a nucleus. In this case, the cross-sectional area of a nucleon, the proton. And the cross-section for PP scattering, where protons come in and something interesting happens of some form, some inelastic process, is roughly speaking 0.1 barns. And so you can see, the rate at which something happens is basically given just by the geometric size of your proton. So you can just think about, I have this proton. The chance that something happens is just the chance that I have projectiles of a given area hitting each other. And so if I take that 0.1 barns, multiply it by 100 inverse femtobarns, and reminding ourselves what femto means, you'll end up getting, with 100 inverse femtobarns times 0.1 barns, you'll end up getting something like 10 to the 16 proton-proton collisions that are interesting, where something happens. And that's a huge number. In principle, a giant data-taking rate, and a giant data set that you can try to mine for interesting information. Sadly, however, it's not, this is a lot of information to parse, but unfortunately, current electronics that we use are not able to actually collect data at this rate. So even though this is the rate at which, or this is the number of interesting collisions we might get in a year of running at the LHC, that's not actually what we're able to process. And one of the challenges that we have in analyzing LHC data is that even before a theorist like me gets involved and says, hey, here's a cool thing that you should try to measure, even before that, there's already decisions to be made about what events you keep on tape and which events you throw out never to be studied again. And so the kind of collision to tape that you can have is much smaller than that whole rate. So actually, before I do that, maybe just to just clarify something. Just if some of these numbers don't seem to work out, here's might be the reason why. So there's a conversion factor that you need to keep in mind, that the proton-proton collisions that are happening per beam crossing you have to fold in together the information about what the instantaneous luminosity is with the data taking rate and the cross section, and then there's a number that corresponds to how many proton-proton collisions are happening at the same time. So this is the number of proton-proton collisions that are happening, but a lot of them are actually happening simultaneously. So if you take this luminosity, again, this 2 times 10 to the 34 per centimeter squared per second, multiply it by the time between collisions, so every 25 nanoseconds, times the cross-section, this 0.1 barns, you'll find a number that's 50. And so that means that each time these beams cross, typically you get something like, at least a current LHC condition, something like 50 proton-proton collisions happening simultaneously. And most of those 50 are totally uninteresting. They correspond to just generic things that would happen with proton-proton scattering. And so if you want to study something like the Higgs boson happens rarely, but when it does happen, it has 49 friends happening at exactly the same time. They're giving you contamination in the event that you're trying to study. And so this is something that's known as pileup. We have a pileup of information that you can't actually disentangle all that 10 to the 16 proton-proton collisions. A question, yeah?
The meaning of 0.1 bar is proton to everything on which process?
Yeah, so excellent question. So what do we mean when we say there's so what I mean is something like non-diffractive production processes. So processes where the proton disassociates in some way. There's an additional contribution from diffractive processes where the proton stays intact. And then there's, of course, elastic scattering, but I want the proton to basically disintegrate in some way. And so this is inelastic. Yeah, for that number, yeah, but it's not so much of a function of energy scale, actually. Of course, if you're at really low energies, you don't have enough energy to do anything to the proton. But that doesn't change so much with energy scale. Okay, so because of these 50 collisions happening simultaneously, the picture, if you'd like, that you get when beams collide is contaminated. And so now if I'm trying to think about how many collisions can I write to tape, taking into account the fact that I have a lot of things going on at the same time, roughly speaking, one collision, which is really 50 collisions simultaneously, is roughly the same size as one cute picture of my son. So, if I take my phone out, take a picture of my kid, roughly speaking, with some kind of compression, you're talking about a megabyte with compression. And similarly, in the collision case, you'd want to do some kind of compression. You want to basically turn off parts of your detector that didn't light up. But because you have this pileup going on, that so-called zero suppression isn't as effective as it might otherwise be if it didn't have this contamination. And so the total data taking rate that I have is 40 megahertz. That's the actual rate at which 40 megahertz, that's the actual rate at which things are colliding, times 1 megabyte. And that gives you 40,000 gigabytes per second. And if you have a fast array of hard drives, gigabyte per second, that's what you can get from a hard drive array. And so that, 40,000, is the amount by which you need to reduce your data volume. Or you just buy 40,000 hard drive arrays, which you can laugh at, but actually the LHCb experiment is going in that direction. They're basically buying monstrous computing cluster capabilities such that in real time they're going to try to analyze everything all at once. But if you don't do that, then you have this data reduction, and that data reduction means that you have to choose a triggering strategy. And triggering is the process by which you decide whether a collision that you have is interesting or not. If it's uninteresting, then you throw it away, and you better hope you made a good decision about what was interesting or not, and that you don't want that data back later on. So then finally, to connect this to what we were talking about earlier with the Higgs boson, so you can ask how many Higgs bosons have been produced? Or are being produced. So if I want to know how many Higgs bosons, and let's say I want to choose a relatively clean channel, so-called diphoton final state. Okay, the number of Higgs to gamma gamma that I would have, what do I need to do? I need to say, how much data do I have? So I take my luminosity, instantaneous luminosity times the integration time, in this case, let's say a whole year. So this is my 100 inverse femtobarns. And I guess, yeah, it's fine. 100 inverse femtobarns, multiply it by the cross-section for Higgs production at the LHC, which is, again, roughly something like 50 picobarns. And then I had to multiply by the branching fraction. How often when I make a Higgs boson does it decay to gamma gamma? And this is, 2 times 10 to the minus 3. And the number that you get is either big or small depending on your perspective. So this number is something like 10,000. And is that a big number or is that a small number? Small? Because you're looking at this 10 to the 16. But, if someone told you, I'm going to give you 10,000 examples of something to study, I mean, you could do a lot of interesting analyses with 10,000 examples of something. So if you can pick out this needle from that haystack, then we have tons of information to do things like precision Higgs studies. It's just that it's buried in this overall collision rate. And then you have to worry, this 10,000, you have to worry that in the process of selecting that you didn't throw out all the Higgs boson events because you thought they were uninteresting. And so you better have electronics that can identify a Higgs-like signature and not throw it out. And this is for me, that's a big number until you realize there's also a huge standard model background for just regular proton-proton making photons through some non-Higgs process. And so that's also something that you're going to have to sift through. So in these lectures, what I hope is that you'll get a sense about how do I go about calculating. So this part, we're done. I have proton-proton beams. I get some luminosity. I have some data. That's the accelerated physicist's job. That's the experimentalist job. If I'm a theorist, I want to be able to predict this cross-section. I want to be able to predict this branching ratio. And something that we're going to spend a fair amount of time tomorrow on is understanding the split between cross-section and branching ratio and where this actually comes about, and show you, how one gets to this factorization between producing a Higgs and watching it decay, and how you connect that to what I said earlier about the fact that you need to sum over all final states that are contributing to a measurement of interest. Okay, so I want to do just one more kind of set of numbers before I show you the kind of master formula for collider physics. This is basically just a rehashing of what I just said in terms of rates, but maybe just a slightly more visceral. So let me just take a bunch of processes. How am I going to do? I'm going to do this horizontally or vertically. You know what? I'm going to. This may dramatically fail. And if it does, that'll be fun. Let's see if I can do this vertically. Okay, so how many lines do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14. So I need to do. Okay, so that's. Oh, great! This is perfect. Okay, so let's see. So 1. Sorry. Okay. Okay, so maybe I should just check that the rest of the lines fit on the other board before I declare victory. 2, 3, 4, 5, 6, 7. Okay. Okay. Good. Okay. So I'm going to do everything in picobarn units. So we'll start up here with 10 to the 12 picobarns. This will be 10 to the 9 picobarns. This is going to be 10 to the 6 picobarns. And then now I'm paranoid. Did I do enough? 6, 5, 4. Let me redraw these to make them. Okay, so if I did this right, this should be a picobarn. This should be 10 to the 3 picobarns. And then at the split in the board, that should be 10 to the 6. So hopefully I did that right. Okay. Okay, so now let's put all the things that I said on this board. So if I say I want to look at the, so this is, so pico is 10 to the minus 12. So this is a barn here. And I told you that the kind of inelastic PP cross-section is here. So this is inelastic proton-proton collisions at 0.1 of a barn. The things that I study with jets, their cross-section has a huge range depending on what you mean by a jet. So the question came up of how do I define a jet? Depending on how you define a jet, the cross-section for making jets, so this is something where I take 2 protons, slam them together, and I get collimated sprays of particles coming out in some way. And you have to define what do you mean by a collimated spray of particles? Is there an energy threshold? Whatever. But the chance of getting a jet that is some evidence of collimation depends highly on your depends highly on your jet definition. So it depends on jet definition. But it's in this range, somewhere there. Okay. And depending on your perspective, everything on this panel is completely uninteresting. And you only start to get to interesting processes like W boson production or Z boson production, or top anti-top production, only when you get onto the second board. And so this is the reason why you need some type of triggering strategy, because you don't want to just collect a bunch of uninteresting events, unless, of course, you're someone like me who loves jets, and then you want to keep everything up there. If you want to dig down into these processes, you either need a triggering strategy or some other data sorting strategy to get down there. And then just adding some other things. Basically, a lot of electroweak processes happen at roughly the same scale, like single top production, WW production, Higgs boson production at 50 picobarns. Is that 50? That's roughly 50. WZ production, ZZ production. Then I'm going off the board, TT bar plus a W, TT bar plus a Z. Eventually, we're going to see off the board TT bar and a Higgs boson. A lot of the processes that we would say are interesting processes within the standard model that we want to study are just orders of magnitude below the things that we're going to be focusing on in these lectures. And so whether or not you care about stuff up here, you have to contend with that as a background, even if you're trying to understand the dynamics down here. So it's a huge range and a range of scales of processes. They're the backgrounds to each other. And the backgrounds to possible new physics beyond the standard model that you might try to look for. Okay, so that was kind of an overview, big picture, kind of in numbers of what we're doing in collider physics. And let me pause to see if there's questions about this before I go a little bit more into the formulas that we use for doing computations in collider physics and a little bit more about QCD. So the question is, what makes these processes interesting? So what makes these processes interesting is that they correspond to the production of new degrees of freedom. So if you're thinking about writing down an effective field theory, and you want to know what are the ingredients in my effective field theory, when you start passing these thresholds, that's when you know that you need to include those degrees of freedom in your effective field theory. And so if I didn't have any evidence for top anti-top production, then I wouldn't know that the top quark was a degree of freedom that I should add to my Lagrangian. And so these processes are interesting to the extent to which they actually are telling you about what new dynamical degrees of freedom are present in the standard model. They're not just interesting because they're rare. I can give you all sorts of crazy jet configurations that are super rare, and they might be interesting for someone who cares about the dynamics of QCD, but they're not interesting to the extent that they don't tell us that we need new degrees of freedom. That even with the existing degrees of freedom that we have, we can have very exotic configurations. But these ones are ones that we would use to establish, for example, certain couplings in the standard model. So, of course, we care about the Higgs boson as discovering something, but if we want to understand, does the Higgs boson talk to top quarks with an order 1 Yukawa coupling, as the standard model tells us, then we would like to look at a process like TT bar Higgs production. And until I see that process, I only have indirect ways of testing whether the top quark couples to top quark couples to Higgs bosons in the way that I expect. But once I see that process, then I have direct evidence for that coupling. Of course, there's indirect ways of testing a lot of these phenomena, but in terms of direct mechanisms, that's what I'm referring to. But in some sense, you as the user get to decide what's interesting. And the thing that I want to hammer home is that you have to decide even what you mean by this cross-section. What do you mean by the TT bar cross-section? And I'll try to explain more later. There's no intrinsic definition of what you mean by TT bar production, not at a hadron collider. It's different at an E plus E minus collider, but at a hadron collider it's ambiguous, and you have to deal with that ambiguity in some way. Okay. So the master formula for collider physics all of our analyses in one way or another are going to stem from this formula that I'm going to write down, which is kind of remarkable because there are certain things that don't obviously fit into this category, but we'll see. So it's a scattering process where I have two beams, let me label them A and B, coming in, and then I have final states 1, 2, 3, up to n coming out. And the master formula, for the purposes of these lectures, I care about computing observables, the cross-section for an observable. You can ask me offline about some recent work that my students and I are doing in trying to go beyond the paradigm of thinking just about observables, but that's not going to be what these lectures are about. There is a geometric factor that will treat our beams as being massless. So this is just, it's more complicated if your beams are massive, but for massless beams, it's just 1/2 times the center of mass energy squared. And then, as I'll emphasize over and over again, we have to sum over all possible final states. So this n has to run from 2, which is the smallest it can be, up to infinity. And you can ask, why can't it be 1? That's a good question. And someone should ask that. You have to integrate over everywhere those n particles could go. So you have to integrate over Lorentz invariant n-body phase space. You have to somehow calculate a scattering amplitude. So the scattering amplitude, what's the amplitude from going from A, B to 1, 2, up to n? You have to square it. And then, as I'll emphasize a lot, we have to choose the observable that we want to measure. And so we have to take that observable, which will depend on where all my various particles go. And this is the thing that I want to compute. And the things that I want to highlight is I really have to consider all possible configurations. If I don't consider all possible configurations, I'm going to get the wrong answer. I have to consider all possible phase space configurations. If I don't consider all possible phase space configurations, I'm going to get the wrong answer. And you have to tell me what you mean. What do you mean by your observable? And you have to be clear about every single phase space configuration, whether you want to include it or not in your measurement. And if you don't, then I don't know how to translate experimental measurements to theoretical calculations. So you want to try to avoid ambiguity as much as possible. And you choose this in a clever way to make to gain insight into something that's physically relevant. So the key that I want you to appreciate is that the cross-section that you measure depends on what you measure. It's pretty obvious. You have to think carefully about this function here. You have to sum and integrate over all possible final states. And this is especially true when we get to jet physics. With jet physics, if we don't do this sum or integral appropriately, we'll just get the complete wrong answer for the rates at which certain processes will happen. And if you don't know what you're doing, you can end up easily getting 0 or infinity for your cross-section if you aren't careful about doing these sums or integrals correctly. Cross-sections have units of area. That's saturated by this prefactor, so the rest of this is all dimensionless. And again, what is our goal in collider physics? Our goal is we have A, B coming in, 1, 2, n coming out, and we want to go from this is the type of information that I would gain when I'm doing a measurement, to an estimate or a calculation of that cross-section. That's kind of the master formula that we're doing for collider physics, and everything else that's going to happen in these lectures will descend in one way or another from this master formula. So that seems pretty straightforward. Why am I making such a big deal about it? The problem is that this 1, 2, 3 up to n, what you measure, these things are hadrons. So these are pions, these are kaons, these are protons, neutrons. But the scattering amplitudes that I know how to calculate, so if I want to do something in the context of at least perturbative QCD, this is in terms of, up quarks or down quarks, up quarks, strange, charm, bottom, top, gluons. And somehow you're going to have to bridge the divide between the types of calculations that we know how to do perturbatively and the type of measurements that we're making, which are made on hadronic final states. And the key will be choosing observables in the appropriate way. And I should say, in some ways, we are extremely lucky. So we're unlucky in the sense that there's a mismatch between what we can calculate and what we measure. But that mismatch is relatively small compared to other possible strongly coupled theories that nature could have thrown at us. So nature gave us QCD, it's complicated, but it's not as complicated as it could have been. We could have been given some kind of crazy quasi-conformal field theory where this mapping would be much more difficult to study. Or maybe the physicists in that universe would be saying, geez, our quasi-conformal field theory is really easy to calculate. How do these people deal with QCD-like theories that have these jets? Like, how do they ever figure out how to do those calculations? So maybe it's just an accident in history that we happen to figure out how to do QCD calculations. But bridging this divide is an ongoing area of research, and I want to give you at least some sense about how we go about doing that. Okay, so this is the master formula. Let me know if there's any questions about this. And then I'm going to remind you about the structure of QCD. Okay, so let me leave the master formula up high. Okay, so what do you probably already know about QCD, but if you don't, I'll remind you. So this is QCD. Turning off electroweak processes for simplicity. So just focusing on Lagrangian of QCD, what do we have? Well, we have kinetic terms for gluons. And we have the gluon field strength. And we have to remind ourselves that there are 8 gluons. So QCD is in SU3 gauge theory. The adjoint of SU3 is 8-dimensional. So we have 8 gluons. 1, 2, 3, 4, 5, 6, 7, 8. And that's the gauge sector, the pure gauge sector. We have quarks. The quarks are the ones that I wrote down before. So we have down quarks, up quarks, strange quarks, charm, bottom, top. And for each of these, we have to write down kinetic terms. And last semester, I was teaching a class on supersymmetry. And supersymmetry is really nice to do in 2-component spinor notation. And so I'm going to write down the QCD Lagrangian in 2-component spinor notation, just because I think it's, well, because I like it. So these are Weyl spinors here. The details of this aren't going to matter for anything in the lectures. Okay, so this is the kinetic term for the quark fields, and then I have to have the conjugate Weyl spinors. And these capital D's here are covariant derivatives. And these covariant derivatives are, of course, ordinary space-time derivatives. But then it also includes a coupling to the gluon fields. And the coupling to the gluon fields depends on the particular representation that the quarks are in. So these quark fields here are really 3-component objects. And these are in a representation where we have 3x3 matrices here. And I'll remind you later on about some of the group theory factors that show up with this TA. And then something that I'm going to ignore a lot in these lectures are the facts that quarks have mass. So the mass term is a mixing between the different helicities of the quark fields. These are my quark masses. And that's it. And somehow, amazingly, the complicated dynamics that we get from confinement in QCD, somehow, amazingly, that just comes from, this. And especially once I ignore these quark masses, it's pretty simple. But the dynamics of this theory is, of course, quite rich. At the level of Perturbative Feynman diagrams, all you'll need to know for these lectures is that we have integration, so in terms of Feynman vertices. And by the way, this whole lecture I'll be talking about things in an off-shelf formalism. Thinking about an on-shelf formalism of all this is something that you'll hear later on in these lecture series, but not from me. We have interactions of quarks with gluons. So this will be a quark field, and let me make it more springy. Springs will be gluons. So we have 3-point interactions, and these are proportional to the strong coupling constant, and then proportional to this TA. So for the 8th gluon, its interaction between quarks is proportional to this matrix. So this is the 8th gluon. We also, of course, have interactions of gluons with themselves. And that's proportional to the strong coupling constant, and then the FABC coefficients, and then there's also 4-point interactions. Getting considerably less springy as I'm going on. Must be the jet lag. And this is proportional to 2 factors of the strong coupling constant, and then 2 of these FABC coefficients. And what we're going to do later on when we actually do a calculation is we're going to take simplified versions of these vertices. In fact, we're going to ignore the 4-point couplings completely. And I'm going to take simplified versions of these interactions that are relevant in the so-called soft and collinear limit of QCD. And when I go to the soft and collinear limit of QCD, it's going to be a lot easier to see the structure of things, but just wanted to remind you what these interactions look like. And this is a flavor-preserving process, so if I start off with 1 quark, it's the same flavor of quark that comes out. And one super important fact that we need to remind ourselves about is that the strong coupling constant runs. So the fact that we call it the strong coupling constant is annoying because it's not constant. It's scale dependent. And so I'll often talk about alpha S, which is G strong squared over 4 pi. And depending on what scale you're probing the theory at, you either have a weakly coupled or a strongly coupled theory. So if I look at the renormalization group evolution of the strong coupling constant, it depends on the number of colors of my theory, which in the case of QCD, this is 3 for ordinary QCD. And then it depends on the number of quark flavors that I have. And this number, depending on exactly what scale you're at, depending on how many quark masses are active, this is something like between 2 and 6, depending on scale. But notably, this number doesn't get big enough to counteract this number. And so this thing is positive. And because this is positive, that means that the coupling constant runs in the following way. But if I'm looking at this as a function of scale, I'm plotting alpha S, the running is such that the strong coupling gets stronger when I go to the infrared. And the scale that's usually called lambda QCD is the scale at which the strong coupling constant basically hits infinity. And that's somewhere around 200 MeV. And so we typically say that QCD confines around the scale 200 MeV, which not coincidentally is roughly the same size as the proton. So we have confinement here. If, however, I'm probing things at the mass scale of the Z boson, which is around 91 GeV, there, the strong coupling constant actually isn't all that big. It's 0.12. And this is small enough that I can do perturbation theory. And so when I go to really high energies, I get asymptotic freedom. Or I get asymptotically a free theory in the ultraviolet. And jets and jet dynamics, and why I like jets so much, is that jets connect these regions. And so the process of initiating a jet starts off in the perturbative regime, where at short distances or high energies, I'm making essentially individual quarks or gluons. But then as that a jet evolves towards the infrared, then my theory confines. And at this scale, then I go from quarks and gluons to the bound states of QCD. So write that down. So at short distances, we have quarks and gluons. And at long distances, we get confinement. And it turns out that the details of confinement actually don't matter that much for the structure of jets. But the constituents of the jets depend on the fact that there's confinement. And we have mesons, which are quark-antiquark bound states. We have baryons, which are 3-quark bound states. There's even evidence for tetraquarks, which involve 2 quarks and 2 antiquarks as the valence structures, and pentaquarks, which are 3 quarks, 2 antiquarks as the valence structures. And if we wanted to, and if I wanted to spend, the rest of this lecture, I could go and explain all the various different mesons and baryon states, the fact that we have spin 0 ones, we have spin 1 ones. For the baryons, we have spin 3 halves. So spin 1 half, spin 3 halves, even higher spin. And then we could start going through all the various group theory structures and talking about, all the pions and etas and kaons, eta primes, and I can keep going. And spin 1, we have rho mesons. And, eventually you learn a lot of the Greek alphabet this way if you write down enough of these states. And here I'm just doing this for effect. There's actually probably no pedagogical value in this at all, except for the fact that protons and neutrons are important baryons for us. But, if you were to ask me at this moment, could I tell you exactly what all the properties of all these objects were? I probably could, because I have the particle data book in my backpack, just in case one of you decided to ask a really complicated question about, what's the delta plus plus? I don't know, but the PDG does. And there's fascinating group theory associated with these objects. And luckily for these lectures, apart from the fact that for some reason I've decided to transcribe everything that appears in my notes, including the omega minus, this detailed structure won't matter. But I want to emphasize that with that master formula that I just erased, the master formula involves these in the final states. It does not involve quarks and gluons. It involves these in the final states. And how the heck can you translate between these objects, which is what you're really calculating the scattering for, and the things that I want to calculate perturbatively, the much simpler, elegant structure of just 3 4-point interactions compared to this giant mess that we have here. And that's going to be something where jet physics will, again, allow us to do this translation. Okay. Questions before I move on a bit? So, let me erase some. So in some ways, it's just kind of amazing that at least at a cartoon level, we really can connect these. And so I'll give you just this cartoon of jet formation, which we'll come back to in the third lecture. That we're going to slam together protons. But as we'll try to see, what we're actually slamming together are the constituents of the protons. So for example, I'm slamming together the quarks, antiquarks, and gluons inside the protons. So for example, I could pluck one quark out of one proton and another quark out of the other one, and they could collide together. And the fact that that's even a sensible thing to talk about, quantum mechanically, actually, you have to worry about interference between a huge number of processes. And so how is it that I can talk about probabilistically just plucking a single quark out of a proton? How does that even make sense? And the reason why it makes sense is because we typically do calculations for these factorized observables, where for factorized observables, it makes sense to talk about parton distribution functions for the probability of plucking a parton out of the proton. That scattering process could create a bunch of things, but at short distances, let's say it makes a quark. And what I can have is I can have perturbatively that quark radiate off, let's say, a gluon. And perturbatively, I can have, let's say, this quark radiate off another gluon, and maybe this gluon splits. And all of this dynamics here is described in perturbation theory. And the formation of a jet is really a perturbative phenomena. It's not restricted just to QCD. QED also with, let's say, electrons emitting photons would also create jet-like sprays. And so we go from our hard collision of partons within the proton. We have perturbative dynamics. And this often goes into the name of the perturbative parton shower, because I have a cascade of more partons being initiated by a single hard parton. Then complications happen, and thankfully those complications don't matter. That the complications that lead to, a bunch of ions and kaons in the final state, if you make the right measurement, then this non-perturbative hadronization only plays a secondary role in the measurements that you're making at the LHC. And then, of course, at the end of the day, these particles actually had to hit your detector. You had to hit the LHC detector, and which are not in these lectures. And these lectures will consist just of the particles that I'll put on the board in a moment. Okay. So we're going to return to this picture later on, but the reason why we have any ability to have perturbative control at all over jet dynamics is because the energy flow of partons, that is, where these quarks and gluons are going from the parton shower, turns out to be roughly the same as the energy flow of hadrons, and that the confinement step doesn't actually rearrange energy by that much. And because of that, you have a chance of actually having predictive control, which approximately is the same as the energy deposits in an LHC detector. And so what this means is that you can make measurements of energy deposits, and those measurements of energy deposits will be linked to the energy flow of partons, which you can calculate perturbatively. But as I'll explain in later lectures, this is not guaranteed. And again, we're kind of lucky that QCD has this property, and QCD is a little bit special having this property. There's other strongly coupled theories that don't have this. But our choice of observable will matter such that I can basically invert this process and get access to information about the hard scattering process. Now, these lectures are going to focus on jets to a large degree, but I just want to make sure that I mention at least all the particles in the standard model. So there are, despite my enthusiasm for it, there are particles that are not jets. There's electrons. Electrons appear in the standard model. They also appear as recognizable objects in an LHC detector. There's muons. Muons, in fact, you have an experiment, the CMS experiment, the compact muon solenoid, where the name of the experiment is linked to its ability to detect this particle. And you have neutrinos, which show up as, they just sail right through your detector, so they just show up as missing transverse momentum in a detector. And you have photons. And you'll note that I missed the leptons. I missed the tau. And I'll put the tau in here, but circle it a bit. Why? Because it's in the column saying it's not jets. Well, actually, it kind of is a jet. It makes a little microjet of a small number of these hadrons coming from the tau decay. And I'll explain a little bit more in a moment. The tau decays fast enough that actually you need to worry about QCD dynamics for understanding the tau. Of course, we have all the particles that give jets. And I left a hole for the top quark. For those of you who know something about particle physics, you'll know that of these jets, the charm and the bottom are special because these are ones that can be heavy flavor tagged, and I'll explain why in a second. But they leave a special signature that makes it possible to distinguish charm and bottom from the other jets. And our fourth lecture will be me telling you about how you can tell the difference between gluon jets and up-down and strange jets, despite the fact that with just standard jet algorithms, they look the same. So you need to do something more special in order to tell the difference between those two. And then we have other particles in the standard model. We have W bosons, we have Z bosons, we have top quarks, which I didn't put in this line for a reason, and Higgs bosons. I'll put them in order, their masses, and Higgs bosons. And these are the heavy resonances of the standard. And they themselves are not jets. However, roughly 70% of the time, they have, each one of them has a hadronic decay. So for example, the W can decay to a quark and an antiquark. So can the Higgs boson, so can the Z boson. The Higgs boson has a 60% branching fraction to BB bar. The top quark decays to a B and a W, but that W, as we saw, can go to QQ bar with a branching ratio that's around 70%. And so all these objects, when they're produced in an extreme kinematic regime where they're highly Lorentz boosted, create things that are called fat jets. I'll explain a little bit more of that when we talk about jet substructure. And so at least 70% of the time, these count as jets. So we have jets in this line, we have jets in this line. And it turns out that if you go to higher energies than the LHC, then eventually electrons and muons start radiating W's and Z's, as do the neutrinos. And that happens, depending on how you count it and what energy scale, like somewhere between, say, 5 and 10% of the time. So eventually, these start radiating W's and Z's, which then create jets. And so even all the things in this line, eventually, when you go to high enough energy, look like jets. So jets are absolutely ubiquitous. That means you can't ignore hadronic final states. You can't ignore the dynamics of QCD. Hence the lecture title, QCD and collider physics. Okay, so I have half an hour. Is that right?
Yeah, maybe.
Or less?
Yeah, 15, 20 minutes.
15, 20 minutes, great. Okay. Great. Okay, so what I will do in the remaining time is, so I'll save this for next time. In the remaining time, I want to reorganize this table. And I want to reorganize this table in terms of the actual particles that might hit our detector. And so this is kind of an experimentalist view of what these particles look like. But it will be instructive to know about this when we start to think about the types of measurements that we'll be doing. And it kind of justifies a little bit the statements that I've made earlier on in this lecture. So we're going to take a tour of the particles that are, let's say, tours of mesons and baryons. And it will kind of explain a little bit about why we build colliders the way we do, why we build detectors the way that we do, and the types of things that we think we can see. Okay, so we're going to organize. So scattering theory, at least formally, we're taking the long time limit. So formally, what we're trying to do is we're trying to measure the long time behavior of a final state when we're trying to do scattering. So you have proton coming in, and we want to know what's the long time behavior, what are the states that I see at t goes to infinity. Of course, our experiments can't measure flows of energy off to infinity, so we have to do flows of energy only to a finite size. The size of the LHC detectors are around 1 meter to 10 meters in size for the various subcomponents. So we're going to have to care not about the t goes to infinity limit, but some finite time cutoff, and use that as an estimate of a scattering rate. And so now it matters then what the lifetime of the various particles that we might produce are, because that would tell us whether they go into the master formula or whether they don't go into the master formula. So we can start off with particles that we think are absolutely stable. And these absolutely go in the master formula. So this is absolutely stable to the best of our knowledge. So protons, to the best of our knowledge, they do not decay. So protons and because they don't decay, you can make beams out of them. So why do we make the LHC out of proton beams? Because protons live long enough that you can accelerate them at the LHC complex and bring them into collision. Electrons, to the best of our knowledge, are also stable. And that's why you build electron-positron colliders, because again, the things that you're making are long enough lived so that you can accelerate them around a complex. Photons are massless, but they can carry significant energy, and without any medium, they would just keep on going forever. And it turns out we know how to make beams of photons as well, so we can make beams of these. And the reason, again, why we can make beams of them is because they are good states to be considering for their long time behavior. So we can imagine making plane waves of them, bringing them into collision, seeing what happens. Of course, there's other states that we have. We have neutrinos, which I guess can decay among themselves in principle. But at least the lightest one ain't going anywhere. So approximately massless. And if we want to connect to Rafael's lectures, we have the graviton, which to our best of our knowledge is a massless propagating mode with two polarizations. And I have no idea how to make beams of those. If someone can make controlled beams of neutrinos or controlled beams of gravitons, not just some black hole merger that's just like spewing randomly gravitons in some direction, but make controlled beams, that would be very cool. I don't know how to do it, but they are, to the best of our knowledge, stable. Okay. And these absolutely stable particles are good for the initial states for a colliding experiment. Okay, so what about particles that are collider stable? What this means is that their lifetime, when converted into a length scale, is bigger than around a meter. And that means that at a typical LHC detector, these things would be long enough lived to hit various detector elements. So the neutron is of that form. And its lifetime is long in the minutes scale. And you can kind of actually make beams of neutrons. They're harder to control because they're neutral, and so you can't use electromagnetic fields to control them, but you can make neutron beams, and people do make beams of neutrons. We have muons. And these things can go pretty far. And eventually we might make beams of muons. We might have muon colliders someday. But because they're so long-lived, that's the reason why we build detectors that are specially designed to identify them. Because they're long-lived, they're relatively clean signatures. So that's why, again, you have CMS being the compact muon solenoid. We have K-long, so the long lifetime state of the kaon. Its mass is, at least order of magnitude scale, similar to a neutron, roughly half a neutron or proton mass. And this is one that lives a pretty long time. It's neutral, so you're not going to probably make beams out of them, but they live long enough that they actually hit your detector. You have charged pions. And charged pions actually have a fairly long lifetime. It has a lifetime of a few meters, almost 10 meters. And charged kaons are a little bit heavier with a comparable lifetime. And these are basically mostly stable on collider timescales. You'd want to make sure you build detectors to see them. Luckily, they're charged, and charged particles are easier to see because you can use so-called tracking detectors to see them. And at some very basic level, these are the only ingredients you need for scattering theory, okay? Because these are the only ones that are long enough lived so that they survive in the t goes to infinity limit, or roughly t goes to infinity limit. And as we'll see in a second, that's not entirely true, that there are other states that you can reconstruct that are shorter lifetime than this. But this cast of characters, I mean, there's some ones that are repeated, but most of these, which are what scattering theory is all about, are not the same as what we have in the standard model states. And it seems a little bit random which particles that I have. So for example, I have charged pions, but I don't have the neutral one. That's weird. I have K long, but what happened to K short? I mean, I randomly selected some of them, and this is what I have to build detectors around. And again, the challenge is that this is what I see, and somehow I have to figure out the presence of all these states over here. So of course, that's not the only states that I care about. There are other states that are kind of sort of stable. Their lifetime when converted to a length scale is bigger than 10 millimeters. And this is where you start to get all these Greek letters emerging. And so we have a bunch of strangeness carrying baryons. They have masses that are in the kind of 1 to 2-ish GeV range. And they have lifetimes which are annoying, so 24 to 87 millimeters. And why is this annoying? This is long enough that they might hit your detector, but not long enough that it does it all the time. And so these objects, when they appear, can just look very funny in your detector. And trying to identify what these are annoying because they're in this kind of intermediate range. They're not definitely stable, they're not definitely unstable, they're kind of an intermediate range. And a particular particle that's in this intermediate range is the K short. And for collider physicists, this is really annoying. It's a state that if I make it, and if I give it a large enough Lorentz boost, it might get into my detector. The gamma factor makes it live long enough. But this kaon has decays that make it decay to pions. I'll explain later. The pi naughts go to gamma gamma. And so these give rise to signatures that can fake the production of some of these states over here. So dealing with K shorts is kind of annoying. And again, you have to remember that whenever you make these things at high enough energy, there's a Lorentz gamma factor, you have a time dilation, and these lifetimes, these C taus have to be multiplied by that dilation factor. So you make a large enough dilation factor on something that's, you know, a reasonable fraction of a meter, it can go be long enough to hit your detector elements around the meter scale. Okay, so then we have a huge zoo of particles, and I'll make sure to post my notes publicly, so don't worry about writing all these down, because I'm not going to worry about writing all these down because there's so many of them. But I'll start writing some of them down. So you have B mesons, you have lambda B's, cascade minus B, cascade BC plus, omega minus BB. You know, basically these are a bunch of bottom carrying mesons or baryons, and some of them even have charm in them. And you know, these are states that have masses somewhere between 5.3 and 15 GeV, and they have lifetimes which are between 0.36 millimeters and 0.49 millimeters. So these are relatively short-lived objects. You give them a large enough Lorentz boost, they travel for some amount of time before decaying, and so that gives rise to this displaced vertex signature, where if you made one of these states, you can figure out that you made it because it traveled for a little bit, a macroscopic link that you can try to reconstruct before it decays. This is for the bottom system. You basically have the same thing with charm. And now I'm getting really lazy. Just write a few of these down. So on and so forth. These have masses that are somewhere between the 2 GeV scale and the 6.2 GeV scale, with lifetimes that span a range from 0.02 millimeters all the way out to 0.15 millimeters. And so depending on where you are in this range, if you're at the higher end of this range, then you end up looking a little bit like this displaced bottom signature. If you're at the lower end of the range, then you don't see a displacement at all. And I didn't leave myself enough room, so I'll have to erase stable particles. But the fact that bottom and charm carrying mesons and baryons mean that when I make a bottom or charm quark and it hadronizes, it gives rise to a state that lives for a certain amount of time before decaying, and I can see that displaced signature. And the last thing that I wanted to put on this, the next one on this list is the tau lepton. And I mentioned that the tau creates a microjet. Why is it? Okay, it's some object with 1.78 GeV of mass, but its lifetime is 0.087 millimeters. So it travels for a fraction of a millimeter, and then it decays. And this is basically borderline detectable if you can see this displacement. And so what you're really seeing when you make a tau lepton is you're really seeing the decay products of the tau, which give you some number of the lighter states which are on this board. Every other state cannot be resolved directly at current colliders. And these displaced vertex signatures are hard. And so the cast of characters for collider physics is just unfamiliar from what we usually think about when thinking about the standard model. But basically all the states up here, these are the states that I should be thinking about when I'm thinking about doing my scattering experiment of A, B goes to 1, 2, up to n. The initial states are the ones I just erased, the absolutely stable ones. The final states are the cast of characters on this board. You have to figure out how you can go from one regime to another. And one state that I didn't talk about is the neutral pion. And I didn't talk about the neutral pion, despite the fact that it has a mass comparable to the charged pion. But its lifetime is short because of the chiral anomaly. So it has a relatively quick decay to 2 photons. And so I never see pi knots directly. Rather, I see 2 photons coming from the pions. And these 2 photons, if they get close together, enough together, they can be reconstructed as if they were a single photon. And at the very beginning of this lecture, I talked about Higgs gamma gamma as being an exciting signal to look for. Well, unfortunately, pions, this can merge together and give you a photon. And you can have a bath of photons coming from the copious production of pi knots that could fake a signature of the Higgs boson. But you never see this pi knot directly, even though you do see the charged pions. Yeah?
Why do you call them displaced vertex?
So it's a displaced vertex because I slam together my protons. If I make, let's say, a B naught, and if I make it with a large enough momentum, it travels for some length. The typical length that it would travel would be gamma times c tau. So if the gamma is big enough, and these c taus are pretty big, and if you have an ability to reconstruct what's going on, this B naught will decay away from where the protons collided. And if you have sense enough instruments that can figure out, by taking all your charged particle trajectories and figure out where the initial primary vertex was, you can infer the existence of these states by the secondary vertex that it would leave. But these links are not so big that this secondary vertex is made inside of your tracking detectors. So you have to basically, your first layer of tracking detectors here, you have to somehow take these. So the first tracking layer is roughly a centimeter away. You have to somehow be able to infer that vertex was present. And not all the decays of these objects allow you to actually infer that displacement happened. Yeah.
You said that these 2 photons,
Yeah.
they can be detected as one.
Yeah.
So like in a master formula, do they have one or 2?
Good. So what's happening in this case? So in this case, I have proton, and if I have a pi naught that's made with a large enough momentum, when you Lorentz boost, you get a relativistic beaming effect. These 2 photons will go in the same direction. Okay? And if your calorimeter doesn't have fine enough segmentation to tell that I have 1 photon here and another one here, if I have a coarse segmentation, then they just light up the same calorimeter unit, and then it just looks like a single photon, which is more interesting than a pi knot. Pi knots, I was going to say pi knots are a dime a dozen, but actually they're probably cheaper than that. So then in the master formula, what do you do? So first of all, strictly speaking, pi naught doesn't appear in the master formula because it decays too quickly. And then you have these photons, and you say, well, how do I count photons in my master formula? And the way that you have to count them in your master formula is that you have to think about every single possible photon configuration that you would count as part of your measurement. So you say, every single possible configuration, I mean, that means that I need to know, like, the intricate details of where every crack is in my calorimeter, and maybe I have different efficiencies for detecting photons in different parts of my detector. You're telling me I need to know that? And the answer is, strictly speaking, yes. Strictly speaking, you have to know all of that. In practice, we don't do that. In practice, we parameterize that with various efficiency factors. But this signature is one that forces you to think about what you want for a measurement. And in particular, what this tells you is that counting of photons is not an easy thing to do. Because whether you have one photon or two, if you don't have the resolution in your detector to tell them apart, you will have to put them together. And so for something like the Higgs boson, where I think you've probably seen the famous plot where you take a diphoton mass spectrum, and you have a falling spectrum, you have a little bump at 125, and you declare victory and get a Nobel Prize. There are various contributions to this. Of course, we have the Higgs signal here. Then we have this continuum background, which is coming primarily from proton-proton to actual two photons. And then there are exotic configurations of just pions doing nasty things to you, where you can have at least some part of this continuum be coming from this type of configuration. This in fact was leveraged when there was this hubbub about the 750 GeV photon-photon excess, which captivated the world for a while, that some clever beyond the standard model theorist actually said, well, maybe I'm not actually making photons, maybe I'm doing something like this, where instead of a pi naught, I have some exotic state beyond the standard model. So I have a heavier resonance that goes to two exotic states beyond the standard model that goes to two photons, but those photons look as if they are single photons. And because you had to think about what the measurement was, you realized, oh wait, yeah, that could be true. It really could be the case that I can't tell the difference between one and two photons because the way that's recorded by my instrument can't distinguish the two. And part of the reason why the LHC was such an advance over the Tevatron was because the detector capabilities were so much better. And for certain cases, you, at the LHC, were able to disambiguate cases like this much more effectively just because of the finer segmentation. Okay. Questions before we wrap up? Okay, so it is amazing to me that despite all the complications that I wrote down, that we've been able to infer the structure of the standard model, even though we have never held a W boson in our hand, a Z boson in our hand, a top quark in our hand, a Higgs boson in our hand. We haven't seen those particles directly, but we can infer them from their decays. And the challenge in collider physics is coming up with what is the mechanism that I can go from a prediction about what the fundamental laws of nature are to a prediction about what measurements that I would make at a collider. And the next 3 lectures, we're going to explore that in some detail. And all these states that I wrote, these are states, some of these were seen, for example, in the old bubble chamber days, where you could actually kind of see those particles directly. Beyond the tau lepton, everything else was inferred. And the fact that we can do that inference is quite amazing. And it's a combination of experimental ingenuity to be able to do things like displaced vertex identification, and then also theoretical reasoning, which we'll explore some more about how is it possible to use factorized observables to go from relatively simple perturbative calculations to these more complicated hadronic final states. And let me say one final comment. If we are really, really, really lucky, then new physics could show up as a long-lived particle that would leave some signature directly in the detector. And there are people who have thought about various beyond the standard model signatures where this whole paradigm that I'll be talking about these lectures are broken because actually the new states that I'm making end up having lifetimes that are within the range of these standard model states. And that would be absolutely spectacular if the new physics showed up in a way where I could more directly see it. Maybe you could have a particle that lives long enough, could actually go into your detector element, maybe even stop in the detector element, decay inside your detector, spectacular signatures like that. That would be amazing. For the purposes of this lecture, I'm going to assume that the only thing that I can see are these states, and then the challenge is how do I go from measuring these processes to inferring the laws of the universe? Okay, let me stop there. Thank you.